I won't read the title for you guys. It's really just the gist of the talk is that category theory can provide sort of constraints on things that we would want to build, whether they're data structures or algorithms or system architectures. I'm going to illustrate that, and the more general claim that category theory is system engineering through three sort of examples. First, data structures. I'll talk about control flow graphs in computer programs. And you see the archive link there. For algorithms, I'll talk about functorial cluster embedding. So some of you may have heard about a fairly recent algorithm called UMAP. This is work that I would have said anticipated it if I had made it public earlier. And then I'll talk about system architectures for sort of robotic mobility in the guise of fast multipole networks. So again, there's an archive reference. You'd want to look at the first version where the categorical language is actually preserved rather than a later version where I stripped it out because reviewers just couldn't grok it. So hopefully as categorical thinking becomes more and more prevalent, that will be less and less a bug and more a feature. One thing that I'm not planning to talk about today is the paper at the bottom, though it does have a lot of categorical flavor towards the end, and I may say some words about it at the end, but the slides don't really cover it. So going into the first part of the talk, flow graphs. So on the left here, I'm showing a computer program skeleton, let's say, in a toy language, where you have various sorts of primitives for control flow, so repeats or whiles or if-elses, and some go-tos, some jumps. So the idea here is that these B's are just predicates, and a S is a subroutine or a statement. So you're evaluating some expression, right? And that or evaluating some subprogram. And what I'm showing on the right is the control flow that corresponds to that computer program. So you start up here. Can anyone see my mouse?
Yeah, we can see it.
Okay, so you start up here, and depending on whether a given predicate evaluates to true or false, you go down the corresponding branch and you run through the program until you get to the end and you halt. So compilers will take the source code of a language, they'll parse it into an abstract syntax tree, they'll do some manipulations on the syntax, and then that will be sort of cross-linked into the control flow graph. And that's how the computer actually organizes the binary code and says, I'm going to jump from this set of instructions to that set and actually execute the program. So in practice, they're quite big, much bigger than this other actual toy example. These are things that I cooked up using a MATLAB script. So a realistic control flow graph, you might have thousands of what are called basic blocks or vertices, or even more. And that's for a single sort of program, not something that calls other stuff. That'll be its own sort of control flow graph. There'll be some other sort of arrow that goes out of this graph to something else and then calls it back in. So they're quite large. That said, there's some tools that let us cope with the scale. So the first is sort of code restructuring. There's a paper from 2004 by Zhang and Dahlender that effectively lets us structure some programs. So you're given in this framework some nasty control flow with lots of go-tos that can lead to sort of hairballs in the control flow. And you'd like to restructure it so that the control flow is as if everything was in terms of if-elses and whiles. It turns out that you can do that. It can be implemented in code. In fact, we've implemented it in code, and Zhang and Dahlender did 16 years ago. And it's quite useful in practice for understanding the structure of code a little bit better, whether you're doing reverse engineering or just trying to streamline or parallelize code that you've written in a way that requires go-to. So for parallel code, that's something that will have to happen quite a bit. So something that shouldn't come as a surprise probably to any of you is that a subroutine is a program in its own right, and a complicated program is built out of lots of little ones. And while it's easy to do that, while it's easy to decompose programs if you have the source code, you've got all these things and you build them together as you compile. Once you have the binary, it's harder to do that. All you have are the instructions, and you know, you can use that to, if you do disassembly, you can get the control flow. That's necessarily a human-driven process. It's fundamentally undecidable. But once you've got the control flow, you then have to say, okay, what parts of this actually correspond to a coherent chunk of the program, and can I sort of abstract this away? That's not just true of computer code, but it could be, you know, business processes. I've seen business processes for companies like Airbus, and they're just enormous flow graphs. As you can imagine, you know, there's all these sorts of very detailed engineering processes, and you might want to say, I want to abstract away certain details of that. And in fact, as far as I'm aware, the best code for doing this sort of thing comes from the business process community. There's some code by IBM, and I think one other chunk of code out there that does this sort of stuff quite well. And they're both coming at it from that perspective rather than from the compiler community. So we saw some control flow graphs already. If we don't have go-tos, it's a little bit nicer. You can see that this particular instance, if you bend stuff around enough, is actually planar, but it's still pretty complicated. And you'd think that these sort of lobes in the control flow sort of ought to correspond to, let's say, subroutines or modules. That said, when this is presented to you, you might be able to eyeball it and see that if it's of, you know, reasonable size, but as the scale grows, you won't be able to. And moreover, you know, graph drawing is also hard. So identifying these subroutines, you don't want to have to do this by hand. You would like to deploy some math that doesn't sort of solve this peripherally. Now, especially here as the scale gets bigger, even though things are planar, it's not obvious that they're planar, right? So, okay, going into some actual math. For the purposes of the talk, we'll say that a flow graph is a digraph that has these unique entry and exit edges and source and target vertices. And if you glue them together, things ought to be strongly connected. So there is a trivial case with one edge that's going to be really annoying and sort of the justification for taking a categorical perspective later in the talk. And there are other cases that aren't allowed that result in what's called dead code. So the example I'm showing down here, if you were to produce its control flow graph, you would see that it doesn't satisfy the requirements above. So the term of art for a subflow graph or a subroutine instantiation as control flow is a single entry, single exit region. So the idea is, again, you've got a digraph and a couple of vertices in it. You know, say that the first vertex J dominates the other. If every way you can get to the source, from the source to this vertex K goes through J. So it sort of sits in between. It blocks, you can't go around it. And that's called dominated. And you can extend that to edges, and if you reverse the orientation of the graph, then you get a dual relation that's called post-domination. So a single entry, single exit region is just a pair of edges so that the entry dominates the exit post-dominates the entry, and the cycle in the graph contains the entry if and only if it contains the exit. So again, think of the idea of gluing the entry and exit edges together and having this strongly connected graph. That's where this cycle relationship or this cycle constraint draws its salience from. So again, you can have a single edge that works just fine. It's degenerate. And again, it's going to annoy us quite a bit later on in this portion of the talk. If you don't have a degenerate case, then you can just talk about the target of the entry edge and the source of the exit edge. And that turns out to be convenient. And finally, if you're doing this in DAGs, it's very easy to compute this stuff. You can literally do it in 3 lines of MATLAB. But in general, it's pretty delicate. Code for dominators is non-trivial at best, and sophisticated algorithms frequently contain bugs, even in like the publications about how the algorithms work. So it's a delicate construction. So one thing that we can do to a control flow graph to try to extract additional structure, and it's a helpful pre-processing step, is really to sort of stretch a flow graph. And so the idea is straightforward. There's really sort of 8 possible motifs that you can have at a given vertex, depending on if you have one or multiple incoming edges, one or multiple outgoing edges, and one or more, or 0 or 1 loop. And for 4 of those, there's a sort of natural way that you would stretch this out, and they're enumerated here. And it turns out it's almost a diagrammatic proof that this operation is well defined. But interestingly, it doesn't preserve planarity. So here's an example. So this is just an aside. So there's a structure called the program structure tree that organizes these single entry, single exit regions. And the sort of critical thing to bear in mind is a notion of the interior of one of these. I'll start calling them SESERS. And I've got a very sort of carefully phrased definition here, and it's very different, or I'm sorry, very subtly different than the original definition from a paper of 1994. And the reason is that in 2012, these folks illustrated that this definition breaks, and this idea, which hadn't had a ton of uptake in the compiler community for reasons that mystify me, I think withered on the vine at this point, because instead of trying to fix the definition, these guys said, well, it doesn't work, and then no one wanted to do it. No one wanted to touch this. You want your compiler to work, and you want the theorems that it's based on to be correct. And it's a very easily patched thing, but nevertheless, it was important to just do this very minor tweak to the definition so that things would work.
Hey, Steve, I just had a quick question.
Sure.
Could you go to the previous slide? So what are the implications of stretching in a program?
Sure. So let's take this 4th motif, for instance, right? Mm-hmm. There's no single entry, single exit region here, right? But if I stretch it, there is. And this would be the single entry, single exit region that says, do this a bunch of times. Or, there might be a subroutine hidden in here. But if I've abstracted it away, it just means I'm going to repeat that subroutine a lot. So there might be multiple ways to get to that subroutine and multiple ways to leave. And that would sort of preclude your ability to analyze this subroutine in its own right, or to isolate it. So the stretching would help you do that, for instance.
Mm-hmm. Oh, and then could you explain to me why the left side does not have single entry, single exit?
Well, there's 3 entries here.
Okay.
So, mm-hmm. And 3 exits, right? Whereas here, there's a single entry in and a single exit out.
Mm-hmm. Okay. Yeah, so that's, okay, I see.
Okay. So if you have one of these non-degenerate SESERs, you call it canonical if you satisfy these sorts of domination and post-domination relations. I'm not going to dwell on what these mean. The important thing is that there's a theorem that the 94 paper proved, and it's easily patched, that these interiors of canonical SESERs are disjoint or nested. And so you can say canonical is minimal, and really it just means that subroutines sit in subroutines. It's like turtles all the way down, or programs all the way down until you get to a basic block. And so there's an obvious sort of tree structure that's formed, and it's called the program structure tree. So the thing I'm not going to talk about here is how you would compute this from the graph structure. It can be done. It can be done pretty simply in quadratic time, and the 94 paper talks about how you can do it in linear time, which is really important if you're doing compiler work. And I found that quite challenging to implement, and I've only ever done the quadratic time algorithm. So anyways, I'll show a few examples. So here's a simple control flow graph. Here is the corresponding program structure tree that's sort of annotated by lines of the program. And then if I coarsen it by in a sense that'll become clear shortly, literally sort of pulling back leaves of the tree, and I use that word deliberately, pulling back leaves of the tree, then I get these other sort of coarsened control flow graphs, pardon me, that really abstract away what given subroutines are doing. So here's another example. And so you've got this reasonably complicated control flow graph and its program structure tree. And once you've coarsened it a few times, you can see, the sort of more salient structure or the higher level structure remains. So here's where categories come in. I'll just recite the definition. So you've got some objects and some morphisms, and you compose them, and they've got the rules that you need. And I'm just reiterating that it is systems engineering as far as I'm concerned. So we're going to see operads, and the idea behind operads is that things plug into each other. The archetype for this is functions on a space, and you just substitute a function for a variable in this way. We'll talk about monoidal categories or tensor categories, so that you can combine objects and morphisms in sequential and parallel fashion. And finally, enriched categories. So the objects are like morphisms. So this category, the putative or notional category of flow graphs that we're going to talk about, has one sort of annoying feature that comes out very early, which is how do you deal with loops? So if you're looking at cobordisms or tangles, and a good reference for this stuff is John Baez's and Mike Stay's Rosetta Stone paper. If you look at cobordisms or tangles, then you can think about how you can sort of piece them together in the right way. But despite the fact that you would want this categorical structure on these control flow graphs, there's a little bit of an obstruction, and it's really the loops. So there's a paper by Ronnie Brown and other folks from 2008 that talks about some of these problems. And the basic idea is that when you identify vertices, you should induce a graph morphism, but if you're preserving edges, you're necessarily inducing loops sometimes. And if you want the loops to be sort of real loops, this is naughty. And so the way that you do it is to differentiate between loops and non-loop edges. And so you get a sort of awkward category that works fine. And I'm sure that probably specialists can do this in a non-awkward way, but that's not me. And once you've got a nice digraph category, you just take this full subcategory of flow graphs, and that's what we're going to talk about. So using the program structure tree to coarsen stuff, we've already seen this, and if I have a couple of vertices in the control flow, I can say, what happens if I absorb one to the other? And so I just do this sort of natural morphism where I map one to the other, and if there's a loop, I kill it in the way that I talked about. And this sort of lifts to absorptions of subgraphs. And once you do that, you get a notion of a coarsening, which I think is the obvious one. It's just you absorb all of these subflow graphs that correspond to leaves of the structure tree. So you could coarsen individual leaves, but it's just that much more notation, so we're not going to talk about that. It's pretty clear. One thing that I do want to mention, though, that is of interest is here's a basic pullback, and for this reason, we can think of this sort of coarsening really as pulling back the graph by the leaves of the program structure tree. So there may even be a way in which you can formalize that analogy, but I'm not aware of it. So there's also an obvious operad, and the idea is you've coarsened stuff, you can go in the other direction, and any place where you've got a node with one edge and one exit, you just say, well, I'm gonna cram another subroutine in there. And again, it gives you an operad and set, and you get this sort of expected complementarity between coarsening and the operatic composition. Also, not a surprise that you can tensor in series. So you've got control flow graph for one program and another. So column A and B, you can do A and then do B, right? That's really all this is saying. And you could do B and then A and so on and so forth. Maybe slightly more interesting is that you can get this enriched category where the objects are the edges of your original graph. And if you take a couple of edges in your graph, the subflow graph induced by them is just the flow graph with entry for the first edge and exit for the second edge. That might be empty. Sometimes it won't be. So, so that's handy because if you were to look at, say, the free category on the graph, just all the paths, well, sometimes you can just get stuck in a loop and you'll have infinite paths. But this category that's enriched is always finite. It's just what are all the subflow graphs, and you can build it using the program structure tree. So that's quite nice. That's not really a surprise. Slightly more of a surprise might be that you can tensor them in parallel. Again, this is something that I think anyone who's seen the sort of string diagrams would expect, but there's some sort of interesting subtleties that have to do with this guy here, the trivial flow graph where you have a single edge. So the idea is you have a couple of graphs and you tensor them by taking the disjoint union and then identifying the entry edges and the exit edges most of the time. So if you have something that's degenerate where you have either the trivial case or the entry and exit edges are adjacent, so you might have edge and then some sort of polyp that branches off and then edge that terminates. If you have something like that, it can be a little bit messy. So this equivalence relation has some annoying details. And that's actually where the lesson is buried for this first third of the talk, which is that these sorts of annoying details and constraints that you say might not appear natural, the fact that they occur coming out of a categorical sort of ansatz or framework is really the benefit. You can say, well, I'll sort of fly it by, or wing it and see how I'm going to construct this data structure, and maybe I'll do some methods that seem like they're the right thing to do. Or I can stipulate in advance that things ought to behave categorically. Go through the trouble at the whiteboard instead of the IDE and avoid a lot of grief down the road. So I know that my data structure actually behaves nicely and it can dovetail nicely with other sorts of mathematically inclined constructions. So just to close this out, the sort of implied tensor on functions really just follows from the one on the objects. So
I have a question about the previous slide.
Sure.
So this monoidal structure, I guess I'm trying to think of it in terms of parallel processing, but if you're talking about maybe a single thread running these two quote unquote programs, you would have to choose which one you do first. So is this monoidal category not symmetric?
It is symmetric. And so it's funny, I should have said this in the slides. The sort of, so there's two ways you can have parallelism, or where you can have this sort of composition, and I'll actually talk about it here. So we talked about sequential, where you just chain them together, and this can be an if or parallel, right? So depending on context. Right, if you have an if-else, you're going to have a branch in the control flow. There's, right, you come in, you branch, and you can have, subprogram in each of these places, and then they'll reconnect. So that's not parallel. It means that there's sort of parallel opportunities, only one of which is realized.
Okay.
And then there's this third motif, which is you've got this sort of primitive notion of a while, and you're going to operatically insert whatever subroutine here. And that's a do while, whatever the orange dot is. So taking these three things into account and using the structured program theorem, you've really got a categorical way for decomposing programs. So I think an interesting exercise, not an easy one, or at least not for me. Maybe it's a thesis of some sort, is to sort of eliminate this sort of modulus that I'm requiring here. So before I go to the next part of the talk, I really just want to reiterate that this sort of categorical requirement that you might place on a data structure really places strong restrictions on them. And that's a feature, not a bug. It ensures that the data structures, first of all, they're not the empty set. You can actually realize them, and that the sorts of things you would do to them are natural, and natural maybe even in the technical sense. So if you want to build a program analyzer, a synthesizer, a compiler, I would argue that it'd be nice to enforce your flow graphs to take this sort of form. And there's various ways that you can make them do that. So I'll move into the next part here, which is more about data analysis, and functorial cluster embedding really comes out of two observations from the literature. First is that there's a class of algorithms called dimensionality reducers, and the sort of archetype for them is principal components analysis. So you have your data, you say what's the sort of Gaussian that best fits it. So you get the ellipsoids from the data, and then you say what are the directions in which the ellipsoid is longest, and those are your principal components. And so you'll project onto those. So that's linear, and it's nice that it's interpretable, but the results are frequently not very useful. So people will resort to nonlinear methods. The downside of that is that they're difficult to interpret. They're sort of everyone's favorite heuristic. So there's some tension there. So it's nice to say that you want a more principled approach for dimensionality reduction. And one is to take this technique of tree preserving embedding, which turns out to be functorial in a way that we'll elaborate on, and then combine it with a classification of clustering schemes. So the relevant paper is by Carlsson and Mémoli. I think it's one of the premier examples of applied category theory. So if you haven't read it, you should. Those two observations are the only original material in this part of the talk. It's not published anywhere. It's not going to be published because it's not a lot of original material, but I think it's worth keeping in mind and disseminating, and I would really love it if someone one of these days will implement this. Maybe it'll be me, but it's non-trivial, and you'll probably see why that is too. So nonlinear dimension reduction, here's an example. You've got the surface of the Earth that lives in 3 dimensions. You can project it into 2, and there's more than one way you can do it. No matter what you do, though, you're gonna have to make some trade-offs, right? I mean, just you're doing some. This isn't a homeomorphism. It's it's not even a homotopy. So you're gonna have to kill some topological information. And this is an opportune place to make a sort of detour here. So some of you may have heard of a recent algorithm called UMAP. So it's about 2 years old. And it, over the last 2 years, has rapidly displaced, or at least competed with, the leading technique for nonlinear dimension reduction, which is T-stochastic neighbor embedding. And this UMAP algorithm was inspired by David Spivak's work on fuzzy simplicial sets. So that's where the sort of similarity comes in, that this categorical data structure would help inspire a dimension reduction technique is very interesting. I think the sort of conceptual difference between this and functorial cluster embedding at a high level is that the distinction between having the data structure sort of inform the algorithm versus, or the categorical properties of the data structure inform the algorithm versus, let's say, the categorical properties of the objective function. And that's what we're going to be focusing on here. So again, I'll cite the paper by Albert Shea et al. And its proceedings in National Academy of Sciences. The objective function is just the single linkage dendrogram. So what does that mean? You've got a bunch of points in a high dimensional space, and you're going to hierarchically cluster them. So you have a point and you say, what's the closest point that I haven't clustered? And you add that to the cluster, and you build up a tree or a dendrogram. And it's labeled with the distances at which you've done these merges. So tree preserving embedding preserves that so-called single linkage dendrogram. And in practice, you have to make some compromises. So when you do this sort of rigid transformation at every step, you'll get a cubic runtime, which is pretty horrible, but it's typical for a lot of nonlinear dimension reduction algorithms. And so the reason why algorithms like TSNE or UMAP are so widely used is actually because their runtime is very low. And UMAP in particular has a runtime that's something like n to the 1.14. It's almost linear time. So you can use it on really large data sets. Whereas something like this, you're limited to something in the ballpark of hundreds, maybe thousands, and there's no real way that you're going to go past that. So it's only really applicable to pretty small data sets where you need a really excellent result. And that's a narrow niche, which is why there's only one implementation that I'm aware of TPE, and why I haven't taken the time yet to implement FCE. So if anyone has a problem where you've got somewhere between 100 and 1,000 data points that you just have to get it perfect, bear this in mind, because this could be the sweet spot. And to that point, we can compare the performance of TPE with TSNE on a few data sets. So here there's some protein sequence dissimilarities between various sorts of creepy crawly critters, some radar signals that are good or bad, and I believe this is MNIST, so just 28 by 28 sort of images of handwritten digits. And so TPE really distinguishes these quite well. You might argue that this isn't great, but compared to TSNE, it's quite competitive. And certainly in the radar and protein sequence cases, TPE really outshines the competition. So getting into the categories, I'm really just going to parrot Carlsson and Mémoli here. So there's three sort of relevant categories. There's the case of metric spaces with isometries, injective maps, and distance non-increasing maps. So another category that's salient is standard clustering algorithm outputs. It's really just partitions of the data set. And the morphisms are things that refine clusters. So again, think of sort of standard stuff that you might see with posets. And then there's a sort of more exotic category of hierarchical clustering outputs. So here the objects are persistent sets and the morphisms are sort of monotone on persistent sets. So what does a persistent set mean? You've got a finite set and some map from the positive, non-negative reals to partitions that gets refined, maybe coarsened? No, refined as you go up, and that isn't degenerate in some way. Right. So think about a hierarchical tree that, or one of these dendrograms that talks about how points are clustered together. This is really sort of an embodiment of that. It's a formalization of how to map dendrograms to each other and when those maps are allowed. So also some of the building blocks involved are equivalence relations. So I'll just run through these. You've got a couple of points in a metric space and some radius, and you're going to say that these 2 points are equivalent modulo r if you can hop from one to the other along some intermediate points that are within distance r of each other. And you can generalize this and say, I'll have a equivalent modulo m and r by saying I'm going to take large equivalence classes and sort of throwing other stuff out the window to survive on its own. So if you have a couple of partitions, again, this is indicating partitions of the data set, and some radius parameter r, and a auxiliary function that's called a linkage that tells you how far apart these two clusters are, and you say that the clusters are equivalent, sort of along the same lines as above. If you can hop, skip, and jump between the clusters in such a way that the distance between the interstitial clusters is bounded by this radial parameter. So we talked about categories, we talked about some equivalence relations. Now we're going to talk about functors. Clustering functor, you go from one of these categories of metric spaces, again, injective, distance non-increasing, what have you, to the space of clustering outputs, and the functoriality is what it is. I won't belabor that. There's a Another notion of clustering functor that's maybe familiar to some of you who have done topological data analysis. It's called the Vittoris-Rips functor. And again, it goes from the same places. The idea here is that you take this point set and the metric structure on it, and it partitions it based on this equivalence relation that we just introduced. And its action on the functions is just what you would expect. And you can sort of generalize this to a hierarchical clustering functor that acts on this mgen, which I believe, just recall, its distance non-increasing. Sorry. This mgen is distance non-increasing maps. And again, it does sort of what you would expect. I won't belabor the details. So I construct these slides so that they'll be useful as references. So forgive me if I blaze through them. Finally, there's this notion of sort of representability of functors. So if anyone's a fan of Yaneda, like holler, I don't really understand it, but there you are. The idea here is that you've got some sort of representing set here, and what it really does is to say, if I've got a couple of points and I want to cluster them together, then this set omega has to be sort of a model for how the points are connected. So the sort of interesting example here is the Vittoris-Rips functor happens when I take this point set omega to be the simplex that are at distance r from each other, or the two simplex. So what is that? That's just 2 points separated by distance r. And if I can sort of place that template down and hopscotch along, then that's that clustering functor. But I might say, instead of taking this little line segment or metric thing, that I could have some more general structure that involves more points, and I can sort of require that it be situated along each interstitial step to cluster things. And that's really what that talks about. So if this set omega is finite, then the corresponding functor is just the unit distance Vittoris-Rips functor composed with a metric changing endofunctor. So we'll see what that means on the next slide. So that's a very important theorem, and it's also essentially unique in this functor, sort of unique in a way, right? There's only one sort of way that you can hierarchically cluster, and everything else is manipulating the data before you bother to cluster. So what is this other part, this way that you would manipulate the data? So I've got some metric space here, and I'm going to act on it. So I'm going to keep the metric space, but I'm going to keep the underlying space, but the metric will change. So this maximal subdominant ultrametric takes a function, w sub x, it's some sort of symmetric thing here, and given that, you do a nested min-max, and that's the result. So in words, the maximal hop and a minimal path between points, and there's a nice little algorithm for it in this Reviews of Modern Physics paper, which interestingly, if I recall, is on spin glasses, and they turn out to have an ultrametricity property that is very interesting anyways. These are obviously sort of technical details. I'm not gonna dwell on them. I'll just say you can unpack the definition if you want, but moving on to something more salient. In a lot of sort of machine learning applications, especially unsupervised machine learning or data analytics or data science applications, you want to do some form of density estimation. And that's a more general sort of thing than clustering, right? If you have a density estimate for saying some point set was sampled from a distribution, then if there's sort of hard boundaries between components of the support, then you're back to clustering. And if you say there aren't these hard boundaries, you're doing soft clustering, or again, sort of density estimation. But the curse of dimensionality means that this stuff is going to be terrible in high dimensions, That said, a lot of modern clustering algorithms depend on this in some way. So dbScan being sort of the most common one, but other ones that are in the literature that are efficient rely on some sort of proxy or outright density estimate. So like work by, I think it's Lio and Rodriguez for, I think it's called density aware clustering, or even affinity propagation sort of relies implicitly on these sorts of notions. And that's not great because, again, in high dimensions, all these estimates are going to be terrible. So you'd like to have some other sort of criterion for picking a clustering algorithm. And so I would argue that functoriality is a good one. And it's nice to have a theorem that says there's only one way to do it. So if you go through the Carlsson and Mémoli paper, they'll draw a lot of comparisons to Arrow's theorem for voting schemes, or the non-existence of good voting schemes. And that if you relax restrictions, you'll get unique voting schemes that satisfy whatever your desideratum is. And this is another sort of example in that vein, where the Vittoris-Rips functor is unique, subject to a few mild restrictions. And if you weaken things to look at injective maps between metric spaces, then you get some more options. I won't belabor this either. But what I will do is to talk about, at long last, where functorial and cluster embedding comes from. So you take tree preserving embedding, and you have some hierarchical clustering functor here that we've seen. And what we'll do is we'll apply this metric changing endofunctor to the space, and then just do tree preserving embedding. So this functorial cluster embedding preserves this this sort of representable functor, since tree preserving embedding preserves the Vittoris-Rips one. So you get this sort of nice separation of concerns where functoriality is preserved at each step. And one sort of interesting possibility is to do the next most obvious thing after single linkage, which is to say require that to cluster things together, that you have these sort of higher dimensional, not one-dimensional simplices that sit in between points that you're clustering, and that's a sort of density proxy that Carlsson and Mémoli point out could be an analog of sort of dbScan, and then when you join it with TPE, you might get something quite nice. So again, if anyone ever implements this, it would be very interesting to do that. If you do implement it, most of the work is building this symmetric function. So there's three things that you need: is that part, and then computing the subdominant ultrametric, but I already gave a reference for that, and an implementation of TPE. But again, you can find R code for that on the internet. So that first part is the hard one, and it's generally NP hard. And so you're going to have to resort to heuristics and or very small sort of spaces, which basically means instead of, if you don't want to blow up your runtime, you're going to have to say, instead of just taking the 2-point metric space as my template, I'll have maybe a 3-point metric space. And maybe it's not a an equilateral triangle, maybe it's something else, but there's only so many triangles out there. So you could think about ways to do this. There's some various things that I've thought through that might be useful, again, if anyone ever wants to actually build this. Again, maybe someday I will, though I doubt it, so I'm not going to dwell on that. But what I will do is try to loop back and say that thinking about algorithms from the point of view of functoriality and category theoretical concerns lets you develop principled algorithms. Not that you're going to use them, but that they're a nice sort of starting point for saying, here's where I'm going to make my trade-offs, or here's where I'm going to relax my assumptions or requirements for the sake of performance or scalability or what have you. And sometimes these things are just hidden. So the folks that came up with tree preserving embedding weren't aware that it was functorial in any sense. And the algorithm's not widely used, partially because of its scaling performance, but I think partially because this sort of attractive mathematical property hasn't been recognized. And so if we, say, if we encounter something that seems sort of elegant or pleasing to the eye, and we say, is there some sort of categorical background to this? It might be you know, might bring our attention to things that could be quite useful. So in the last few minutes, I'm going to talk about system architectures and what I'm calling fast multipole networks. So I'm interested in this from the point of view of teams of lots of robots, or autonomous systems of systems. So there's three things that sort of come into play here. And there's the global structure, right? A bunch of agents interacting. So anytime you hear global structure, you think topology. There's going to be emergent behaviors, and that makes me think of statistical physics. And you're going to have to compose these teams or systems, and that makes me think of category theory. So in my experience, it's quite rare to, sorry, there's a typo here. It's quite rare to see applications of statistical physics with either of the other two fields. One thing that would be a nice application besides the present one, and I'll mention it to anyone who's looking to do or propose a dissertation, is to black box Glauber spins. So some of you may be familiar with work that Blake Pollard and folks have done on black boxing Markov processes, and a Glauber spin is a special kind of Markov process. It's like a toy model of a magnet, and you would like to say, well, if I have two magnets and I put them together, there's a composed system, and meanwhile the dipoles in the magnets interact, and that's sort of the tricky part of a problem like this, is figuring out how that sort of magnetic interaction ought to be realized in a categorical way. So my 2 cents, that's a great PhD topic. So anyways, in the last minutes, I'm going to talk about a way that all three of these sorts of fields or properties might usefully contribute to an architecture. So when you have teams of robots, you might sort of model them as simplicial sets. When you do data fusion, you might try to handle that with sheaves. We're not going to talk about that. We're going to talk about the sort of statistical physics perspective and operads. So in terms of the statistical physics perspective, there's something called the renormalization group. So the idea is you've got some theory given by a function f, you've got some data and parameters, and you're going to coarsen your data, and you want to say, do I have a theory that still acts the same way if I coarsen the data and change the parameters somehow? Does the theory still act the same sort of way? And if that's true, your theory is called renormalizable, and that's actually a requirement essentially for physical theories that aren't called effective. So any fundamental physical theory has to be renormalizable. And that's actually the principal obstruction to quantizing gravity, is that gravity is not renormalizable. And so any sort of quantum theory becomes just plagued with infinities. So if you look on the NLab, there's a lot of very fancy talk about renormalizability. And I think Kevin Costello's work is really where this stuff is all unpacked. I don't understand it, but I can tell that it's complicated. There's all sorts of fun stuff with Feynman diagrams and operads. So those of you who parsed Olive Saul's talk, which I wasn't able to stay on for the whole thing, but if you were on board the whole time, that's probably right up your alley. We're not going to do anything that fancy in the last few minutes. I'm going to take, for my F, for my theory, I'm going to do a weighted average. So for my data points, it's going to be a bunch of just points in space, and I'm going to weight them in a natural way. I'm going to cluster these points. So that's sort of, you know, functorial in its own right. And finally, I'm going to do some sort of renormalization of probability distributions. So here's the idea. I've got a bunch of point masses, and if I'm far away from them, they all act like one mass, right? So if you're in the Andromeda galaxy, the Milky Way is like a point mass. Or if you're in Alpha Centauri, the solar system's like a point mass. So the way to formalize that is by using something called the weighted little disks operad, or, you know, this is something that many of you have probably encountered in the literature, and there's a natural weighting that you could put on it. Just say, I've got some masses associated with this and some masses here, and if I insert this into this gizmo here, well, I just take the proportional masses and sort of chop this fella up. So if you take that and the notion of the sort of standard potential for the Laplace equation, so 1 over the surface area of a sphere, or whatever you want to call this Minkowski content, you basically get, you know, Newtonian gravity sorts of stuff. So, or let's say electromagnetism, where every charge is the same sign. So here you've got some sources and weights. You can think about this sort of like charge, if you like. So that sits in Euclidean space across a simplex, and you're going to use these and form a sort of weighted sum of potentials. And in the far field, it's going to look just like the potential overall. And there's this sort of natural way that you can approximately plug things into each other and maintain their structure. So it's not quite an operad, but it's something that's very operad-ish. So what? Well, we're going to model systems of systems with this sort of framework. And the idea is we're going to have a bunch of robots or a bunch of agents that can communicate efficiently or plan efficiently. And if we add or take if we put agents in or take them out of the picture, that it's not going to present some sort of problem. So the framework can't be very rigid. And we're going to want to have the sort of framework that could accommodate sort of parallel considerations, like what tasks do you give these robots? So we actually talked about something that would work there, this sort of flow graph operad. You know, we might need some annotations that are geometrical in nature to do motion planning, but again, we're going to be addressing that. They might be constrained, so you could think about constraint problems like Boolean satisfiability. These can sort of plug into each other too. You know, or again, teams could be simplicial operads. So I won't belabor that so much as get into the meat. And looks like I have 8 minutes left, so all right. So there's a few classic techniques for motion planning. One of them is artificial potentials. And the idea is basically treat obstacles and goals like they are charges. And
Steve, sorry to stop you. Actually, you have about 20 minutes left. We stop at 3:15, so you don't have to rush super fast.
Okay, well, don't worry. I've got stuff that I can rant about or entertain questions. So
cool.
So these agents are treated as if they're electromagnetic particles in a sense. They can say, well, I don't want to be next to someone else, or I want to go away from this thing or towards that thing. And the sort of nice feature of this approach is that since everything's harmonic, you don't have local minima. So there's not a place where you can get stuck for a long time. You may have something that you'll get sort of delayed in, but all the theorems are sort of nice. There's a little problem with that monopole operad construction that if you try to incorporate sign terms, things seem to go nuts. So again, exercise for the audience is to explore that and see if there's something interesting that can be salvaged in an operatic sense. When you use this motion planning approach, you've got to do a lot of complicated geometry and represent it in terms of a function. And so the approach is to sort of distribute sources along little panels that then form the boundaries of places where you want things to go. So we'll see an example of that soon. But before we do, I'm going to talk about the sort of underlying algorithm that motivates a lot of this work. And so the fast multipole method is really a way to do simulations of gravitational or electromagnetic interactions that are hyper efficient. So if you think about what does it take to do a simulation of a bunch of particles interacting gravitationally, if you have n of them, each one feels the influence of all other n particles. And so a naive simulation is going to take n squared time for a single time step. You're going to have to do n squared calculations to figure out where these particles are going to go. So the reduction from n squared to n is really remarkable, and so much so that it got a lot of attention as one of the best algorithms essentially ever. It's based on two key ideas. They're sort of approximate renormalization in a sense, and one is you're going to represent clusters of particles with these far field approximations, and it's just a multipole expansion. So you take the Laplacian and you do the harmonic analysis of that operator, and you'll get all these spherical harmonics or what have you, and you're going to use that expansion to say what happens in far field and truncate in a way that is very controlled, and that gives a a predetermined error bound. And if you're close, if you're not in far field, well, you just interact the way you normally would. And so that sort of idea relies on decomposing space to have these well-separated clusters of particles. So it works for homogeneous potentials and logarithmic ones. I think that the term of art is something roughly like a Gelfand homogeneous potential of type something or other. There's some rather exotic construction that lets you think of a logarithm as a power law, and I think Gelfand was the guy that sorted it out. And there's nice ways to do this and super fast, and you can find it on some of the biggest exascale computers in the world, and that's great. But at the end of the day, it's really matrix multiplication. So here's an example. I'm taking a bunch of these panels that I discussed, and I've got a square here, and I'm distributing charge according to the color indicates the sign of the charge. So red is one sign, blue is the other, and the transparency or opacity indicates the sort of strength of the charge. Right. So these robots really want to get away from their starting place. You really want to kick these birds out of the nest. And there's this obstacle here that you don't want them to bump into or get stuck, and you want them to end up over here. And I've deployed a bunch of agents as just sort of test particles. So 80% of them uniformly distributed up here and 20% down here, just so that we can see a little bit of structure. So when we run the fast multipole method on this, it does this sort of discretization of space. And what I'm showing here are just the counts of the test particles per region. And there's the accompanying quad, the corresponding quad tree. So that tree that we just saw, it's really decorated with these truncated multipoles that I talked about, right? These spherical harmonics or what have you in 3 dimensions that represent the particles in far field. And if you were to say I need absolute precision, I won't tolerate any error, then this quad tree would just be homogeneous, right? Everything would be down to its lowest level it would be as fine as it could be at every point. So the sort of art is in avoiding that work. And in particular, the fact that in practice, the topology of that tree doesn't depend, and I mean topology not in, let's say in the homeomorphism type of the tree, right, where the actual shape of it really does matter. That doesn't depend on the values of charges, except in an extremely weak sense that for all practical purposes we can ignore. So we're going to use this to build some networks or virtual communications backbones that sort of dovetail with the little cubes operad and motion plans. So as an aside, it smells like this sort of thing ought to be extendable to sort of cases where the potentials are just fundamental solutions of elliptic PDEs. So exercise for the audience. Here's how we build one of these fast multipole networks. So I'm showing the same points, the same sort of scenario that you saw in preceding slides. And in the background, you see the discretization of space that's induced. And for each of these nodes, we're going to say, if you're in the same leaf box, we're going to connect all of you, right? So here's a simplex, and here's a simplex. So all those dark blue things are simplices that belong to the same leaf box. You could do something more sparse if you wanted. I'm just doing this for simplicity. So in fact, if we did something more conventional here, you actually might get some improved performance in terms of the metrics we'll show later, but it wouldn't really align as well with the sort of concept of the fast multipole method. So the idea is to have the same sort of construct apply equally to motion planning and network backbone construction. And so this sort of respects that. Then for each box, you say, what are the boxes that are next to it? And I'm going to connect the nearest neighbors in adjacent boxes. So that's these cyan or turquoise edges. And finally, anyone who's just left alone, I'm going to connect them to whoever's closest. So that's the red things here. So when you do that, we'll compare it with some other candidates for network communications. And what I'm going to do is restrict this graph and all the other graphs so that the edges are of the sort of minimum are at or below the length required for everything to be connected. So we could do this over a number of lengths, but right now in these examples, I'm going to fix that. So this is right at the threshold for connectivity. So here's the sort of restriction of that fast multipole network to omit edges that are longer than that. And what I'm showing over here is what's called a random geometric graph. So this just says for those points, anything that's below that radius, any pair of points below that radius, get an edge. So you connect everything that you can that's in range. So there's a lot of edges there, obviously, and it probably isn't very efficient from the point of view of communications. So you could say, let's try to do something sparser and use what's called the Delaunay triangulation to reduce the sort of pointless duplication of comms links. And we'll see that that does better. And then you could say, let's take what's really the de facto state of the art for a network backbone. And it's a further subgraph called the Gabriel graph. These things are a little bit delicate to build, and that in fact is one of the reasons why you would consider something like a fast multipole network, is the fact that these are delicate to build and that they don't really dovetail as cleanly with the motion planning aspect. So we're going to look at the performance of these sorts of networks from a number of perspectives. So we'll look at how many edges are there, how many connected components, what's the degree distribution, really sort of basic metrics. A more interesting metric is the efficiency. So you look at the inverse distance between 2 points, and you take an average of that over every pair of points that aren't the same. And you can do that for a Euclidean metric or a hop metric, where every edge has a cost of 1. And an especially important thing to look at is efficiency per edge. So we're going to normalize that by how many edges there are. You can also talk about energy, and so that in that sense, in 2 dimensions, you would just square the distance between or the distance of any link and sum those up. That's for sort of unidirectional, as if you're communicating via, say, laser or focused electromagnetic energy, say, like multiple input, multiple output sort of thing. You could do omnidirectional, which is just, you say, how much energy does it take to send out a sphere of photons, and we can talk about efficiency per energy. So that's one thing that I'm not going to talk about is how hard is it to form these other networks. So it's going to be harder for Delaunay or Gabriel graphs to form these than for a fast multipole network. And if things are moving quickly, if your communications backbone is sort of an issue to begin with, then you don't want to have to sort of have 2 different architectures serving cross purposes. So that, I think, is actually where the potential power of this approach lies. So let's take a look at the numbers. So I'll just walk you through these. It might be hard to see the y-axis. So the colors are the same across all of these panels. The black are the restricted geometric graphs, i.e. everything gets thrown in. The red are the restricted Delaunay graphs. So sort of, first reasonable thing you might try. The magenta is the restricted Gabriel graphs, or the sort of the state of the art restricted to a given radius. And then blue are these restricted fast multipole networks. And what I'm doing in each of these panels is I'm saying, what is the radius of the restriction? And so, i.e., how far can I transmit, and what's the graph that comes out of that? So I'll look at a few things. First of all, how many edges are there as a function of increasing radius? Well, eventually these things saturate because there's sort of geometrical constraints on where the edges can go, but they just keep coming for the geometric graph. Note that that's log scale. The connected components, as you increase the radius, sooner or later everyone can talk to someone nearby and everyone becomes connected. So the connected components go to 1. The efficiency, the Euclidean efficiency stabilizes at some point. The distance between things isn't helped by adding more edges. And the hop metric efficiency isn't so nice because, in the case of the geometric graph, there's sort of always more you can do until you've hit the diameter of your point set. So you can already see that that's, again, not a great strategy. So once we talk about these lower panels, we're talking about efficiency per edge. And this is for Euclidean metric and for the hop metric. And so interestingly here, this sort of, when we talk about the hop metric, this is a point where the restricted fast multipole network actually looks like it outperforms the restricted Gabriel graph. So it outperforms the state of the art for this metric. And it's not an unimportant metric, right? It costs something to put edges into a network backbone. And the metric that you usually care about isn't how far away it was, so much as how far did you have to go. Light speed is fast, right? You usually care about routing and computation rather than transmission. So this is actually a quite salient metric. And by that metric, this approach is actually better than the state of the art. So we'll look at a few other metrics just very briefly. Degree distribution, they're all roughly comparable except for this ridiculous one. The sort of total energy budget, again, all sort of comparable. And we can talk about efficiency per unit energy for omnidirectional and various choices of metric. And as you might expect, in most of these cases, the state of the art is that for a reason. It performs the best with respect to almost all of these really salient metrics, but not all of them. And the one that it doesn't is one of the ones that operationally is quite interesting. So with that in mind, you could say, you're directing these robots towards some end, and you want to do that in a hierarchical way. I like to think of this in terms of an operative goals. So we've got this framework for networking and motion planning, and we've seen a sort of operatical perspective that informs it and in fact motivated it. It would be interesting to say, how far can we push these considerations? Can you take networking and motion planning and add on things like tasks or constraints or composition of teams and so forth? So to the extent that you can, you might really start seeing a lot of synergies in terms of the architecture that would result, because the math would keep things as clean as possible and no cleaner. The argument that I would make to all of you is that these three notions of topology and statistical physics and category theory are going to contribute to the development of multi-agent systems in the real world. And some of the work in the broader community is pointed in this direction. So there's various work that folks have done on realizing categories of Markov decision processes. And one thing that I am personally interested in and trying to nail down is whether or not there's a nice objective function for something called intrinsic motivation that is a functor with various nice properties. So in this setting, you've got some robotic agent and it's got a world model or multiple agents, and they've got a model of the world, and their intrinsic motivation might be something like maximize the number of things that you can do an hour from now, or maximize the channel capacity of a channel of a notional communications channel where your inputs are actions that you take now, and your outputs, or the things you receive, are the results of a sensor in the future. There's lots of different flavors of this, and so you might say, well, if I want this to be functorial, that might help you narrow things down. So for those of you that have seen work by Tom Leinster and Tobias Fritz and John Baez on functorial properties of entropy, this would be in that sort of vein and sort of more constructive in nature, where you say, I have these desiderata or these ansätze, and I want to try to find what the appropriate objective function is. So I'll circle back to the thing I started with. Category theory is systems engineering. So you've got my organization details up here. That's me. These are the papers. And if there are questions, I'm happy to entertain them.
Well, thank you so much. That was a great talk. So I'll allow people to unmute themselves now. Please don't, grief us. But if there's any questions for Steve, please unmute yourself and ask now. I think actually I could probably get some dibs on this. I have a question, and I'm trying to formulate it as well as I can. But when you were talking about the flow graphs at the beginning of this, you were talking about identifying subroutines by looking at like the lobes. So is there a way with this more operatic approach, I guess, of identifying subroutines as like, yeah, in an operatic sense?
Yeah, so there's an algorithm that does this. And it actually, the program structure tree really is an algorithm rather than a data structure. So let's think about the example of a DAG. In that case, it's pretty straightforward because what you can do is just talk about the number of paths that go from one place to another. And if you require that the number of paths that go from A to B is the same as the number of paths that go from B to A when you reverse things. Actually, I think I'm saying something wrong, so forget that. I'll just say that there is an actual algorithm, and the original version of this paper on the archive has a bunch of MATLAB code to compute this. I think it's for an older version of MATLAB than the current one, so it doesn't use the graph library, and that makes things sort of hard. But if you know MATLAB in 5 minutes or so, you can get that stuff working and work through examples that are in the paper. And if you're really good, and you dig up the original work by Johnson, Pearson, and Pingali, or if you look for open source stuff on they usually call it the process structure tree when they're actually computing stuff these days because of where it's being applied. You can do this on very large scale processes or programs for that matter. The algorithm's pretty intricate. It relies on something called I think I might get the acronym mixed up. I think it's an SPQR decomposition. And as far as I know, there was not a correct implementation of it until 2000, even though the algorithm was first described in 1975. Like there were bugs in the papers, there were bugs in the implementations, and so it's just graph theory, but it's a pretty intricate algorithm. And I think, in fact, the only, or if not that, one of the only places where you can find the correct implementations of these algorithms are in the process structure tree code.
So maybe I'm falling into the same pitfall of considering these flow graphs as data structures as opposed to algorithms. But it seems as though the hierarchical clustering scheme that you mentioned midway through the talk requires like a metric structure. But it doesn't seem like there's any sort of metric structure or inherent metric structure on these flow graphs. So how would you do sort of a hierarchical analysis with regards to the clustering?
So I don't know that I would try to cluster the flow graphs per se, so much as that they're hierarchically organized. So you're given a flow graph that's really big, right? And it has hierarchical structure. So the program structure tree and the associated algorithm pulls out that hierarchical structure. That's really what it does. So one thing that I will say, sort of as a tangential remark, is if you talk about clustering programs or algorithms, that's a very interesting question. And it's a very useful one. So you might think about like saying, you know, are these two pieces of code, one of which I've seen before, and it's a virus, is this other piece of code a virus? That's essentially a problem of clustering a function or an algorithm. And any sort of, even clustering functions is going to be undecidable because equality of functions is undecidable in any sort of, you know, reasonable class of functions. You add to that the notion that what does an algorithm actually mean? The definition is very poorly formulated, although I noticed that you have Noson Yanovsky coming to talk, and in my opinion, he has the best definition of algorithm that's out there, which is it depends. And there's a sort of Galois or order theoretic way in which you might say, you know, these different notions of algorithm might be the one that you want. So clustering at that level, where you actually have the annotations on the flow graph, is extremely difficult, extremely rewarding. There's a huge payoff if you can do it well, and it's extremely useful. If you don't care about the annotations and you just say, I want to cluster the graph structures themselves, then you could use an edit distance of whatever sort. So Evan Patterson, and I think, you've at least seen this work because we saw it at the same place. Evan has done some work on building metrics, Wasserstein type metrics on functors from a small category to set. And so one of those things can be, a quiver, and a quiver, a special class of quivers is just a flow graph, right? So you might look at sort of traditional edit distance on graphs. That's expensive, but Evan's approach has the virtue of relaxing to a linear program, which might be quite useful. And I imagine that sort of stuff is going to see a lot of use. So, did I leave anything open there?
I think you covered sort of what my question was about. Thank you.
Hi. First off, great talk, Steve. You made a small comment about intrinsic motivation all the way at the end.
Sure.
I was wondering if you had is this like the subject of current work you guys are doing? In terms of finding a functor to represent intrinsic motivation, or is it you're kind of describing a project where you're applying kind of like the functorial entropy approach to thinking about how roboticists think about intrinsic motivation, like that literature?
I wouldn't say anything like grandiose in terms of like it's a dedicated effort. So I will say it's something that's been on my mind for a little over a year. I've talked with David Spivak and Brendan Fong about this, and they pointed out why one notion of intrinsic motivation called empowerment is not functorial. It has all these sort of nice algebraic properties that you might want, like with respect to sort of sum and product of direct sum or tensor product of things, but it abjectly fails at compositionality, which I had seen these sorts of algebraic things and piqued their interest, enough for them to entertain talking to me about it based on those sorts of algebraic relations. But it turns out that the sine qua non, the things that the requirement that things compose nicely, isn't satisfied by that. And that's what's sort of maintained my interest here. So I have a particular sort of idea that I think is the right one. And I'm, let's say I'm in spare moments, I'm slouching toward that effort. But
okay. Cool. Yeah. I mean, I don't know if there are any. I guess maybe I'll ping David and Brendan at some point and see you. I just mentioned this. I asked the question because I know like almost like 6 years ago, Gromov was actually really interested in intrinsic motivation and trying to find a functorial characterization of it.
Really?
Yeah, it was just kind of a surprising thing. It was just like we had a series of conversations. He was really interested in intrinsic motivation because he met Oudéer, who's a roboticist based in France. Oudéer, he's one of one of the big theorists, I guess, who does this.
Okay.
And he was really interested in sort of find a mathematical, a more like a higher, I guess, a categorical version of that.
Misha Gromov.
Yeah, Misha Gromov, Gromov.
Wow. Yeah, I will say that so I'll let the cat out of the bag a little bit and say that the thing that I think is the right answer is something called transfer entropy.
Huh.
And I haven't written this up in anything close to like a mathematically reasonable form. It's barely something that a physicist would tolerate. But it smells to me like this has, like it's actually linear under direct sum and has the sort of, nice behavior under tensor that channel capacity or empowerment inherit from it.
Mm-hmm.
So, so I think that's the right answer. It's a little bit challenging to sort of articulate what what this thing is in terms of categorical language. So I think it's like at some point, like just to deal with the tensor and some stuff, you start having to talk about like I think it's a right coax rig category, right? Which is
That sounds about right.
well, yeah, which is not like very, it doesn't really capture what you're trying to say, which is that this is natural. Then why is it such an esoteric construction that you're having to invoke? So there's some tension there, and frankly, it's hard for a dilettante like me to navigate the NLab and to unpack things in a way that is efficient to make this stuff work. So as I go forward in that, I'm going to try to just stick to the algebra, and so stay tuned.
Makes sense. Yeah, please keep me posted. Or I find this stuff super interesting because I also did some work as a roboticist way back when.